Okay, good afternoon everyone. I'm really pleased to see so many of you here. Okay, so let's get started. Can you hear me? Or do you? Because this is not a microphone.
That's just for the recording.
Yeah. Okay, my name is Arne Førlie, and I work for the missile division at Kongsberg Defence and Aerospace here at Kongsberg. And in today's talk, I will give first an introduction to some of the products where we use C++. I will talk about our C++ coding standard and how we handle.
Can you speak up a little, please?
Yes, I will do that. Okay, I will talk about our C++ coding standards and how we handle the different C++ standards. I will give you an insight into some of the challenges of developing software for decades and what practices we use. And I will talk about the tools that we use for this. Okay, this is a naval strike missile, which we normally named just NSM. It's an anti-ship missile. It can be launched from both ships and from different kinds of trucks. It has a solid fuel booster that accelerates it out of the container and until it reaches cruising speed. At that time, the booster is jettisoned, and the small jet engine takes over and until it reaches the target. The other product we have is a joint strike missile, the JSM. It's a continuation of the NSM, but it is air-launched from the F-35 aircraft. Since it's air-launched, it has a speed already close to cruising speed, so it doesn't need a booster, just a small jet engine for propulsion. Some of the details of the Joint Strike Missile is that it's about 4 meters long and weighs about 400 kilos. At the front, we have an IR seeker, and we have some wings. This is an air intake for the engine. At the rear, we have some actuators, so ailerons that are controlled by actuators. The wings are folded during storage and are unfolded very, very close, very shortly after launch. At the rear end, you can't see it, but the computers are somewhere here. The range of this thing is about, well, it could be more than 555 kilometers. That's 300 nautical miles. And it depends on the launch altitude. And the speed is, as I said in the title, it's high subsonic. In a missile project like this, there are lots of technology to be integrated. We have inertial navigation. We have GPS navigation. They are aided by terrain profile matching. We have imaging homing, flight control, flight route planning. For the computer, we're using a multi-core thing. And we also have thermal control, because inside the weapons bay of the F-35, it's really warm. So the electronics needs liquid cooling. And to get rid of the heat, we actually use the missile's jet fuel as a heat sink. The product is very software intensive and has been estimated that more than 60% of the system requirements affect software. The computers that we use are custom made for our purpose because they need a special shape and size. In addition, there are some environmental requirements, such as operation at very low temperature and very high temperature. For the NSM computer, which is kind of old now, we use 15 PowerPC computers, CPUs. And they have in total less than 2 gigabytes of RAM. And for that, we use the PSOS operating system, and we use a DIAB compiler, which supports C++98. The JSM uses 2 each of the PowerPC Core IQ P4080. That is an 8-core CPU, so that gives us a total of 16 cores. And we use the Integrity 11 operating systems from Green Hills on that, together with the Green Hills multi-compiler, which currently supports C++ 14. We started using C++ in 1995 because at that time we started development of the NSM. We had a lot of experience with C in the Penguin missile, the one up in the left corner, but we knew that NSM would be larger and more complex than anything we had done before. So we didn't think that C was high level enough, and we had no experience with Ada in our division. And there was a lot of internal lobbying for C++. So we decided to go for C++ in 95. Okay, what you see here is a glacier, and it moves slowly. And that is something like development of military products. It takes a long, long time. So the NSM software development started in 95. It's still actively maintained. We're adding features based on customer requests. And we think it's going to be maintained for at least 20 more years. The JSM development started in 2010. And we have developed and worked on this for 8 years, still haven't finished development. But when development has finished, we think it's going to be maintained for 30 years. So it's a really long lifetime of everything we do. Our organization follows a model-based systems engineering principle. So our systems engineers, they make models of everything in SysML. And we get the 4 views into the models. We have the requirements view, functional, logical, and behavior. And from this, the software engineers make models in UML. The way we go from UML to executable code is shown in this figure. For instance, at the top we have the UML interfaces. We generate IDL files from them. IDL is Corba IDL. And from them again, we generate C++ interfaces, including ORB client stubs and server skeletons. Similarly, from the UML logical and physical architecture, we generate XML files that are Corba component model compliant. And from them, we generate C++ component configuration files. And from the UML component design, we generate C++ state machine skeletons. And the thing here is that the information flows from left to right. So when we find a problem in the executable that could be traced back to the UML interface, we go back and update the UML interface, and then generate new IDL, which then generates new C++. That's the way. So the good thing about that is that the model doesn't grow stale over time. If you just update the source code, the model will just grow stale. But we are kind of forcing ourselves to go from left to right, left to right. Of course, there's a feedback when we find a problem, but it's a manual feedback. There's no automatic round-trip engineering or anything like that. It should also be said that we don't really design the components very much here. So if you find a problem in the hand-coded C++ functional code down there, we don't really have to update this. It's an application that provides functionality and has primary value. And that's where most development effort takes place. We therefore try to make it really easy to develop the application code. We also have as a goal that all application code should be 100% portable between platforms, whether it's running on a Linux workstation for testing or whether it's on the real missile computer. So all communication, synchronization, and thread safety issues are taken care of by middleware within the runtime library. I have a small figure here showing kind of layers. We have the operating system at the bottom, some abstraction layers. Then we have this runtime library, the green thing, which the application code relies on. Because of that, the application task can assume that it runs in a simple single-threaded environment always. And the application task is not allowed to use any OS mechanism such as a mutex or semaphore or anything like that. And it's always going to be run to completion. That it's not allowed to do any blocking calls. If it has to wait for something, it has to start a timer and wait for the timer to time out. And okay, in order to get some platform independency, we have these abstraction layers. So we have both an operating system abstraction layer that takes care of threads, times, clocks, network things. And we also have the hardware abstraction layer, which kind of abstracts away the hardware peculiarities. We follow an incremental and iterative development process. So we go through this cycle of planning to maintenance many times. So now I'm going to talk about some of the tools we use for implementation and testing. Our products are built from reusable software components, and for the JSM flight software, I think it's built from something like 200 components. But when we take into account simulators and test stations, we probably have 300 components. And we use, we version every component independently from other components. So therefore, we use a multi-repository approach to our source code management. And we also have this thing that the software components are provided at source code only. We do not build precompiled libraries, and we do not put them, since we don't build them, into any kind of artifact store. The only exception to that are some large third-party components, such as Qt, that we use for simulators and test stations. We put them as precompiled binaries because it just takes too long to build them on demand. Workspace management. We like to do things simple. So all development is done in activities and tasks. An activity has a dedicated workspace, and all changes are done on a dedicated branch in the version control system. And an activity has a lifespan from a few hours to a few months. When we are starting a new activity, we create it together with its workspace by means of a tool which we call Shaman, change management tool. We then have so it's kind of as simple as this. You just do Shaman make activity -p, the ID, and some suitable comment, and then you have your workspace. And that one has all the components, and all the components are of the correct version. So Shaman kind of has a lot of metadata telling what versions are supposed to be in this. To build our software from source code, we use a build system that we have developed ourselves. We call it HiMake. It's cross-platform and Linux, Windows, and it supports native builds as well as cross-compiles to Integrity and PSOS, for instance. It generates make files from simple build files written in a declarative language. The dependencies between components form a directed acyclic graph. And this gives many positive effects. One of them is that HiMake will detect if there are any cyclic dependencies between components. So I just given 2 examples here, how to build. If you want to make a native build for a Red Hat 7.5 64-bit computer, you just do that, HiMake -G and -P. If you want to build the exact same product for the missile computer running Integrity 11, you use the second line. HiMake is involved in a lot of our tool integration, and thanks to its directed acyclic graph, there's a lot of things we can do with it. We generate all the documentation out of it. We generate JSON compilation databases used by Clang Tidy, and we generate project files for other static source code analysis tools, and a lot more. And this shows one example of a build description file. This is an easy one. It specifies at the top that this component has one IDL3 file, IDL Interface Description Language version 3. And then it states that this component depends on another component. So behind this HMK IDL3 sources, there's a rule that knows how to generate all the makefile statements so that the following transformation happens. So we start from the left with the comp.idl. It's run by the IDL compiler, which generates 5 files. And we can see one of them at the top is actually an XML file, but we use the ACL2 suffix. And that one is run by the ACL compiler. It generates 2 files. And then we can see that C++ file and that C++ file are compiled by the C++ compiler. They are put into a library by means of the archiver. So for the user, he just makes one statement, and all of that happens by magic. We don't specify anything by absolute paths or relative paths. Everything is specified by means of identifiers. So when I set up a dependency there, I just made use of 2 identifiers. HiMake also takes care of transitive dependencies. So if component A depends on component B, which again depends on C, the header files from C are made available to A. Life was kind of easy when we only had C++ 98, but starting with C++ 11, the pace has quickened up, and we get new C++ standards every 3 years. And we think it's good because we have this opportunity of writing simpler, better, and more safe code, but we just have to adapt our practices a bit. We used C++ 98 for, was it 13 years, 14 years? So we kind of got really used to that. So we still want to be in control, but we have to be more agile to be able to take advantage of the new language and library improvements. So we have a C++ coding standard. It is inspired by the Joint Strike Fighter coding standard and the LMTEL rules and recommendations. But I think our standard is more permissive than most other standards for mission-critical software. So we allow almost everything C++ supports, like multiple inheritance, RTTI, templates, the standard library. We allow exceptions, but only for exceptional situations. We do not allow dynamic memory allocation from the heap, except for during the initialization or startup phase. Then, of course, we can use a heap. Since we are not allowed to use the heap after initialization, we have made quite a few container classes that are not dynamic in size and can be created on the stack. So we have things like a bounded string and bounded vector class, and then fixed size array. We have also dedicated pools for message buffers for communication. So, and then we have overloaded the new and delete operators so that when we allocate the buffer, they go to that dedicated pool. We have to take into account several compilers, and they are not in step feature-wise. For instance, the Greenhills multi-compiler didn't support C++14 until early 2018, and that was about 3 years later than GCC had full support. So if we wait for all compilers to support a certain standard before we allow it, there will be a lost opportunity cost. So our pragmatic approach is that we allow different code to use different C++ standards. So our simulator software that only runs on Linux using GCC was the first to use C++11. It was the first to use C++14, and they are now on C++17. But sometimes a feature not supported by all compilers sneaks into the code base. But so far we don't consider it to be a big problem, because we integrate often and early, and we use Jenkins to build our software in all kind of combinations of compilers and C++ standard. So it's kind of caught really early. And here I've just shown you some examples how we use HiMake to build the same code with different compilers and different standards. So we have some native builds here, and now specified GCC 720, and then Clang, and different standards. And the bottom, how we use it for the missile computer. When it comes to code optimization, we have this principle: we only do it where necessary. So we have put some effort into optimizing our communication middleware. And we have done some micro benchmarking, measuring the cost of making a remote procedure call from A to B. And on the target computer, we are using the Greenhills Supertrace probe to investigate possible bottlenecks. And I'm now going to show you some of that. Okay, the Greenhills Supertrace probe, it's a trace tool that is connected to the PowerPC P4080's Aurora port. It can do real-time hardware trace of all instructions from one CPU core at a time, and it can collect up to 4 GB of trace data. You might think that 4 GB is a lot, but depending on what the core is doing, that could be just a few milliseconds. To visualize that trace data, the Greenhills, they provide a tool that is called the Path Analyzer. We have used the Path Analyzer and the tracing tool to optimize collection class, a container class, that we found out it initialized itself twice. And we also used it to optimize an algorithm where large data structures were copied instead of moved. And that actually gave a 50 times speed up of that algorithm. So that's meant we could do things in a few seconds instead of minutes. This is what a trace in the Path Analyzer looks like. At the bottom, you see this kind of blue line here. That shows we're doing remote procedure calls again and again and again and again. And from all that is about 3 milliseconds. That's a whole trace. The detailed view above shows about 27 microseconds of that. And it shows where, by me, you see the background color. There's some green. That is the client task doing something. Then we have the pink. That is the server class doing, the server thread doing something. And then we have some white background. That is when we are running in kernel. What you see up here are the different functions making calls. So you have kind of, let's say, function A doing a invocation to B, to C, to D, to E, to F, to G, and so on, and all the way down. And I think this one shows about call depth about 25. Yes?
Can you use this to look at your stack? Like how deep the stack is? Like if you've allocated enough stack, for instance?
No, not the stack usage.
Yeah.
We have other tools to look at the stack usage. This is just the depth.
So,
Yes?
so I might be missing something, but when you say remote procedure calls,
Yeah.
isn't this run one computer?
Yes. Actually, well, no. Okay, we have two CPUs, each having 8 cores. Yeah. We have allocated those 8 cores. Sometimes we have an SMP. All 8 cores is one SMP. Or the other one, we have actually 3 AMPs having 1 core each, and then we have one that have 5 cores. And then when we do remote procedure calls, it's between these kind of computers inside the same CPU. Yeah. So, and we have, when I say remote procedure calls, it's a CORBA call, and it's go through not TCP or UDP. We have a kind of custom-made transport mechanism. Did that answer your question? Good. Okay. Okay, here I have zoomed into just one RPC, and we can see that the client is doing a call, doing something, then the server, the pink side runs, and then it's back to the client. And when I was doing this, I was not really looking for anything in particular. I was just doing an exercise, well, to learn the tool. And I got curious about that part of the trace. And that is, it's hard to read here, but that is the default constructor of a fixed size array class. And I think you can see it's doing something here, and then it's doing something there. And I'm going to, and this is the declaration of that class. As you see, it's very simple. It's very similar to what is probably a stud array now. It's an array of some element type. So when we zoom into this, this is just a constructor. It's about 6 microseconds of execution time. And, oops, I thought I had, that was the wrong one. There we go. Okay, this part here, it's where we are default constructing each element in the array. But what was the second part? That one. Okay, then we go and look at the implementation of that constructor. The first part we saw was obviously the default construction that happens there. And then when we look at the code, we can see we have an explicit loop again to iterate over every element and construct it again. And that shouldn't be necessary. So we rewrote it like this, where we only added that one, deleted the loop, and the extra execution was gone. Our software is tested and tested. At the bottom level, we have the unit tests where we currently use Google Test and Google Mock. I'm not going to say anything about that. There have been at least 2 talks about that during this conference. In the missile integration lab, we run our applications on the real missile computer using real hardware components. We have test arenas that simulate the actuators, sensors, and all the environment. And of course, the software runs in real time. And this is as close as real flight as we can get in the lab. We also have a missile simulator that runs on Linux workstation with in simulated time. Now I'm going to show you a video of one of the test flights. It's Royal Norwegian Navy frigate that fires a missile. You should see that the booster accelerates the missile out of the canister and how the wings are unfolded. It has an inert warhead, so there's no explosion when it hits the target ship. And some of the video is really disappointing. And some of the video is filmed from a jet fighter flying chase. That means it tried to follow it. So now we should see the wings unfolding there. That was no explosion. That was just debris. Okay, compiler policy. The compilers and their configuration are tightly controlled by the build system and the version control system. So we like to know exactly what we're using, and for this reason we never use a compiler that comes with a Linux distro. For the Linux, the build system currently supports 3 versions of GCC for Linux. We also support Clang, and we support the compilers for our embedded targets. We started using GCC in 2004 when 3.3 was the current. At that time, we believed it was a good thing to keep the development environment stable. So we didn't upgrade the compiler until 2011 when 4.5.2 was current. And that was not easy. The new compiler gave us didn't give us problems, but it rejected a lot of code that the old compiler thought was okay. And we decided then we don't want this experience to happen again. So for the last 6 years, we have installed one new GCC compiler every year. We normally do it in January, because that is when GCC has released the 0.3 version. That gives us a nice cadence. We start the new year with a new compiler. And since then we give the developers 1 year to adapt to the new compiler. So we have normally 3 GCC versions rolling. We have the previous default, we have the default, and the next default. The multi-compiler that comes from Greenland is updated about once or twice a year, independent of GCC. For each new compiler version, we enable a few more warnings. That is a pragmatic approach. If we want to have a strict compiler, but if we increase the strictness too much, the developers will either give in or the project managers will say that there are no money to fix the issues. So we just make it a little bit strict every time, every year. The build system provides 3 predefined warning levels. The default level, where the code should always be warning free. We have the strict, where it should be warning free at the end of the year. And we have the pedantic, which I don't think anyone uses. And we think this is a way to continuously adapt and improve the code when it's supposed to live for decades. If we don't dare to follow the world outside, we will very soon have code that is old again. We have found out that our current warning levels are stricter than what most third-party components are built with. For instance, const correctness is an issue. The multi-compiler from Greenhills issues warnings if a variable could be const but isn't. So in the beginning, we got thousands of warnings from third-party components from Boost, Qt, and Google Test. So we have now configured the build system to suppress that kind of things. For GCC and Clang, we use the -i system directive when specifying the include file search path. For the other compilers, we have implemented filters inside the build system that suppresses warnings based on regular expressions. The whole point of this is that the warnings should never be visible in the console or the IDE. There should be, even though the third-party component has issues, the user should never see them, because our goal is 0 warnings at the build line. We also use static code analysis tools. We have QSC++ from programming research. That's a commercial product. It has thousands of rules that can be enabled and disabled individually. And recently, we have also started using Clang Tidy from the LLVM project. We originally introduced Clang Tidy as a tool to assist in modernization of our code base, because Clang Tidy comes with 24 modernization checks. I'm not going to tell you anything about Clang Tidy, but they have these kind of checks that have a name, and when I just filter them on modernize, there are 24. Then you can run a command line that looks like this. The ... is one or more source files, and then it will automatically fix or modernize your files. And if you want to improve the code in other ways, there are 268 other checks. Some of them are not really relevant to us because they are according to the Google coding standard. But we have found that, for instance, the readability checks are really good. Clang Tidy requires a JSON compilation database to work, and our build system, HiMake, generates that one for us. So this is an example where I have run Clang Tidy with the modernize using check. And I hope you can see that what's happened here in this header file is that the type defs have been replaced by the using keyword, which is the modern way of doing it. Here I have run the code with the readability container size empty and redundant string C-string checks. And you should be able to see that the original code had if commands.size equal to 0, which has been replaced by commands.empty. And there are some redundant calls to C string, which are just gone. We also use a number of runtime analysis tools. We use Valgrind. We use address sanitizer that is part of GCC, undefined behavior sanitizer. And we can activate them through simple switches to the build system. For the target computers running integrity, we have various resource analyzers to monitor memory usage, heap usage, thread stack watermark, and CPU usage. We also use tools for test coverage like SquishCoco and some profiler tools. Finally, I'm just going to show you what we do about C++ source code beautification. We think that having uniform formatting of source code improves code understanding. Having a tool doing it removes some of the subjective "I like it this way" discussions and "I like it that way." So what we've done is we have using two tools called uncrustify and A-style. So they work together to format the source code to our standard. Uncrustify does 95% of the job, and A-style fixes some of the remaining issues. It should be said that uncrustify is a bit challenging to configure because it's got more than 600 options. But it also means that whatever your coding standard or coding style is, you can actually adapt the tool. We have integrated the tool into our code editors and IDEs. You can also run them from the command line to format whole directory structures at the one time. We have looked into Clang format, but so far I think that the uncrustify A-style combination do a better job than Clang format. But I also think that Clang format has more potential in the long run. This is an example of what the tool has done. I would say the code on the left is a mess. The indentation is crazy, the placement of the braces is crazy. But on the right, you can see it has formatted all the bracing according to the Allman style that we use. You can see that member variables are aligned. Let's see if I can see them here. Okay, this one, like this, it aligns on the equal operator, equal sign. Now also align the delete and default on the standard functions. So having a tool doing all this means that it can actually be quite nice code. Normally it's too much manual work to do this kind of alignment, but when the tool does it, there's no cost. And I think the code is more readable like that. Okay, thank you. Are there any questions? Yes, Mike?
Does your coding standard say anything about which parts of the STL to use or not use?
No, I think we allow all of STL.
Okay. Yeah. Except the stuff that uses dynamic memory.
Yes. And we are allowed to use the during initialization we can do it.
Yeah.
So, Yes.
How do you catch whether you're actually doing dynamic memory stuff after initialization?
Good questions. I should probably repeat the question. How do we catch that we don't do dynamic memory allocation afterwards? Actually, we don't have any tools for that. So I think it's code review that are supposed to catch them. Yes?
You're saying you're creating IDL. Are you actually using Corbit on target as well?
Yes, but it's our own real-time object request broker. It's not a commercial product. It's very, very special made for our purposes. Real-time, yeah. Yes?
Slightly out of context, but if you happen to miss the target, what happens to the missile?
Okay. Okay. I think
Terminated or
no. Okay. Okay. No. Okay. Okay. I can probably say something about that. Okay. The depends on the mission, but I think the missile is you can configure it to do a what do you call turnaround? Retarget. Okay. It flies. It finds out I missed the target, so I make a turn, go back, and I don't know if that can be repeated, but I think eventually it will just find out I have to do something safe, and that is to dive into the water. Yes.
Are the hardware and loop tests, are they automated, or is this something that is done manually?
The tests.
You mentioned that you have hardware in loop tests.
Oh yes.
Are these automated?
Okay. Our hardware in the loop tests, they are kind of halfway automatic. There's always a person there observing the experiment or the test, because something could go really wrong, like smoke coming out of the devices and things like that. But they are scripted. Yeah.
But then how do you you use the sensors, so how do you provide inputs?
We have simulators outside, and they are kind of what was the word? This okay. We make a mission, and then the simulators follow that mission to simulate whether we're going simulating GPS positions, whatever, and that just goes into the system. I must say that the real-time or the hardware in the loop simulation part is not my expertise. I'm sorry about that. Yes?
real-time or near real-time software?
Near. I think our goal is we have to keep up with the sensor inputs, but if we are 10 microseconds late, doesn't really matter. The aim is to keep the missile stable and follow its pre-programmed route, but it's not really critical if you are a few microseconds late. Yes?
Are there any external classification societies or someone who needs to approve the software process or the entire level, or like in a commercial flight?
Yes. Okay. There are. Okay, we do not have to follow anything like RTCA DO-178B, which are used for civilian avionics, but we always have to go through a safety board with the customer, and particularly I think the US have a really tough safety board, and where we have to prove somehow, I'm not involved in that process, that our software is safe.
I think that was it.
Yes. Okay.
Thank you.
Yeah. Thank you.